So this example here is from the iris data set here, where you can see the two features are there, petal length and petal width for species 0, the class 1. And you can see the contours for the Gaussian is tilted upward, right? Which automatically gives us the idea that it's positively correlated. And if you see the covariance value, so these are the variances, but if you see the covariance value, it's a positive value. So we know it's a positive correlation, right? So in a sense, what we are saying is if you increase, generally speaking, in a flower, if the petal length is high, the petal width will also be relatively higher, right? And here in this two case, we are seeing that the one of them, so petal length, the mean is 4.96, the petal width, the mean is 3.43. And of course, based on these values, we can also find the correlation, right? Based on the covariance between the two features is 0.12. So we can use the definition of covariance divided by the standard deviation of 1 times standard deviation of 2 to find the correlation, right? So this will now become the correlation. So yeah, any question at this point? So also one more thing where we stopped, I guess, last time is if you have this contour and the contours are something like this. So we understand now that this is negatively correlated and the covariance would be something a negative number, right? Similarly, if we have no tilt, then we know that there is the correlation is 0, the covariance is 0 in that case, right? And we spoke about this also, the idea that if the features are independent, the covariance would be 0 and the correlation would also be 0 in that case. Okay. But the opposite is not true, that zero covariance or correlation does not guarantee independence. Good. So if you have no more questions, I'm going to go forward now. So let's take this thing here. So the thing is now, how does the PDF look like, right? So we are speaking about how does this PDF of P of y given x, P of y given x look like in the 2D case, right? So this is where we stopped at. So what we look at is that in this case, what happens is same idea. You have 2 pi, but now the variance, which was there, the standard deviation, now it is a covariance matrix, and this is a square root of the determinant of the covariance matrix, right? So square root of the determinant. So this is determinant, right? Determinant of the covariance. And it's a square root of that, and times e to power of, if you remember last time, it was minus half, then you had x minus mu square over sigma square, but because now you have two features, you'll have x1 minus mu1, x2 minus mu2 transpose the covariance inverse times this x1 minus mu1, x2 minus mu2. So I'm sorry, this is what we get now, right? So this is our PDF for P of yeah, so I'm sorry, this is the PDF of P of x given y. P of y given x is nothing but P of x given y into P of y or P of x, right? So just make it clear, of course, probability of generating x given a class y. I'm sorry, yeah. So this is the value. And if you see here, of course, this is again, let's come to this point. So this is again normalization thing, right, for the probability. And this is same idea, right? So this is exponential distribution, and the value would be highest once this is 0, right? So x1 equals to mu1, and x2 equals to mu2. That would be the peak point, right, in the distribution, and it will be e to the power of 0, and then the PDF would be only this value. Okay. Now to just also make sure that the whole thing at the end gives you one value, right? So if you see the dimension here, this dimension is going to be what? Is going to be, I'm sorry, this is going to be 1 times 2, And this is inverse of a covariance matrix. So this is 2 times 2, and this is 2 times 1, right? So if you see, if you do this calculation, let's say you do this first, you get what? 2 times 1, and 1 times 2 multiplication, this vector, you get basically, if you multiply this, then you get 1 times 1. And then you have the minus half there. E to the power minus half, a scalar value is still a scalar value, and this whole thing is also a scalar value, you can see, right? So determinant is one value. Of course, in the 2D case, you have your determinant is whatever you can say AD minus BC, right? So if you have A, B, C,
Professor, I got a question.
Yes, please.
In the page 21, it says this equation is P probability of x1, x2 instead of probability of x given y. Is there a difference?
In page number what?
Page 21.
21. Let me open it. Okay, yeah, I'm just trying to see this. It's telling in general the PDF. Yeah, okay. The point here is it's the same thing. Now your x is a vector, right? What I'm saying, P of x given y, x is not a scalar value, it's a vector. You see this here. Can you hear me?
Same thing, everything's similar, Doctor.
Exactly,
Also,
that's what I'm saying. So x is not a scalar value, so it's a vector consisting of two items, x1 and x2. So what we are saying here is P of x1. So it's saying this is dependent on two values, the two components of the vector x. But actually, the general formulation is this same thing, exactly the same thing. Not only the difference is x is not one value, it's two things, right? So you're saying the PDF depends on x1 and x2, which is part of the x vector, the vector x. So it's the same thing actually. Is this clear?
Yes, clear. Thank you, Doctor.
Okay, very best. Very good. Okay, so this is again, we find out that this is just a value. The whole thing becomes a value, right? So let's look at some examples here. So this first example here, it says both these two distributions here, it has mean of 1, 1. And let's see here. In this case, the covariance matrix is 4, 0, and 0, 1. So, and this time, this is something different. So let's first look at this first case, the first case. So what we see is that the covariances are 0, which gives us the idea that both the features in this case are independent. Is this clear? And the variances, right, is 4:1. In a sense, we are saying that the first feature, let's assume this is the first feature, x1, and this is x2. So the spread of the first feature is higher than the spread of the second feature. If you speak of the standard deviation, it will become 2:1, right? So you're speaking about the spread is 2 times 1 in that sense, right? Now, if you look at the second case, second example, again, we have these two features, x1 and x2. OK, and now we see a positive value for covariance, which means that there's a correlation between them. It's a positive correlation, right? So that's why the tilt is upwards. And again, the same thing, the spread of x1 feature is higher than the spread of the x2 feature. So looking at this, you can say this is positively correlated features. These are independent features because your covariances are 0. Good. So again, if you apply this to the iris problem, instead of now using one feature, if you use two features, these are the results you can get. So you see here, these are the three things. You see, at least by using two feature, one of the class is almost nicely separated, right? The green dots. But still, the two classes are still the other two classes are still having a lot of overlap. But now your error rate goes from 26.67 to 22.22. So it's a reduction, but of course, it can be even done better. So any question at this point, how we use this generative classification with two features? Because then if we understand that, we'll move to the general case, the multivariate Gaussian, where you can have any number of features. So if there's a question, let me know, otherwise I'll move forward. Okay, so it seems everything is fine. So now let's move to the concept of multivariate Gaussian, right? So let me just get my things right. Yeah. So in the multivariate Gaussian is just the generalization of what we have been discussing so far. So now we are speaking about any number of features, not just one or two features, right? So the question would be what changes? So if you see the first component, what we estimate from the training set, is the priors of a class. So which is exactly the same, nothing changes, right? But now your mean vector has how many components? The mean vector mu has components depending on the number of features you have, right? So you'll have mu1, mu2 up to mu d. So this is your mu vector, right? Assuming you have d dimensions, the features have there d components to the feature x, right? And then what happens to the covariance now? Same thing. So covariance is again a square matrix. The size is d cross d, right? And it's something like this. So you have the variance of the first feature, the diagonal ones. The diagonal are the variances of the individual features, right? And what about the non-diagonal one? This is covariance of 1, 2, the feature 1 and 2. This is 1, 3, and so forth. And similarly, this is covariance of 2, 1. So it's still symmetric, right? So it's still symmetric, but these are the covariances here. And the diagonal items are the variance. So it's a d by d covariance matrix, right? So again, if you have the training samples, basically you have to estimate these three parameters: the prior, the mean vector, and the covariance matrix per class, using the samples of each class individually, right? Per class. And then what would be the normal, the general PDF thing? So what you're saying is P of X. I try to use black, it's much clearer on the screen. So what is P of X given Y? And again, keep in mind, X is not one value, it's a vector, right? So all these components of the feature X. So what you get now is 1 over 2 pi d by 2. D is the dimension, right? Dimension of the feature vector. D by 2, the determinant of the covariance matrix, square root of it, e to power of the same thing, minus half. What do you have here is x minus mu. It's a vector, right? It's not one value. X minus mu is a vector. So x1 minus mu1, x1, x2 minus mu2, and so forth till x d minus mu d. So you have this vector transpose covariance inverse x minus mu. So this is the general form of the PDF, right? This is what you get for the d dimension features. So again, just to make sure that things make sense, again, here 2 pi d by 2 is the same thing. It's not a different thing. If you remember, in 2 dimensions, d is 2. So 2 over 2 is 1, and that's why we just write 2 pi. And in case of 1 dimension, d is 1. So 1 over 2 is square root. So we wrote 1 over square root of 2 pi. So again, it's the same form. But of course, if you have more than 2, d being more than 2, the general form is 2 pi to power d over 2, right? And same thing again, what we are speaking about, this is the normalization thing for the probability. And these are the exponential one. And this, let's try to see the dimensions here. So what we are speaking about, x minus mu is a mean vector, right? And if it's transpose, what happens now? You get a dimension 1 times d. And this covariance matrix of d dimension, so it's d cross d. And again, this is d cross 1. So if you do this multiplication, you end up with a scalar value. E to power raised to a scalar value is still a scalar value, and the whole thing is again a scalar value, right? Is a PD, the probability density function, the likelihood of x given y. So any question on this formulation or the standard form of the Gaussian? If you have any question, let me know.
Yes, regarding the inverse of the covariance,
Yeah.
isn't there a possibility that we cannot find the inverse?
Yeah, that's true, and that's something we'll see very soon. What will happen? So we do something called smoothing. So because the point is that the covariance matrix is a square matrix d by d, but it could be that it's singular, right? So you might have to do some smoothing. So this is something interesting as an insight. We'll discuss it very shortly. Yeah, so we have to treat that.
Doctor, what is a sigma and the denominator? Is it a determinant?
It's the determinant, exactly. The determinant, the square root of the determinant.
So it should be scalar, yeah?
Yes. Any other question? Anyone has any question?
So, yes. So how do you also cope up with the expensive computation of the inverse of the covariance matrix?
Yeah, of course, that's there. But what happens is once you have your training samples, yeah, so that's part of there. So you have to do that. So the covariance you calculate it once, but once you have these features, you are doing the actual testing. You have to deal with the inverse. That's there. Yeah. Any other question? Okay, so if no more questions, again, so this is what basically you have to do in the general form. So assuming that in the iris dataset, actually it's a total of 4 features. If you use all the 4 features, you train your priors, which will not change actually from 1 or 2 features. You have the mean vector for every class, you have the covariance matrix for the every class. Then you apply it for the test samples using this PDF. You basically get the test error drops from 22.22 for 2 dimensions to 4.44, which is quite good, right? So using all the 4 features, you can get almost like close to 96% accuracy on your test samples. So now let's try to understand this, these multivariate some more details, right? So one of the thing is some special cases. So let's take the first special case. What it speaks about is the idea that what if you have independent features? What will happen in your general sense if you're using this generative modeling and your features are independent? So if your features are independent, we understand that the covariance matrix, I'm sorry. Okay, come on, yeah. So what will happen is, who is going to tell me what happens to the covariance matrix if your features are independent?
It will become very sparse because of the covariance
Sparse,
will be
right?
0.
So basically, yeah, exactly. So what happens is now it becomes a diagonal matrix. So you have only the diagonal elements, so sigma 1 square. So variance of the first feature, variance of the second feature, up to variance of the D features. But all the non-diagonal elements are 0 now because the features are independent, right? So if the covariance is this pair of 2 features, but all of them are independent, so all of them are 0, right? So this is also in a short form is written sometimes as a diagonal matrix sigma 1 square comma sigma 2 square till sigma d square. So this is something an interesting insight. What happens is also what about the inverse of this? So inverse becomes also very easy, right? So the inverse of diagonal covariance is nothing but 1 over sigma 1 square 1 over sigma 2 square until 1 over sigma d square. So even this is easy to calculate, right? The most important thing is now think about it. If your features are independent, what happens to the number of parameters in your model? How does it compare as compared to you have d dimensions of features and the features are not independent? You end up with very few parameters, right? So basically what happens is, of course, you have one prior and the mean vector in the general case, right? So if you're speaking about the general case, you're speaking about you have for the mean vector you have d values, d parameters, and for the covariance matrix you have d square parameters, right? Of course, one part is half of the other, you can say in that sense, right? It's symmetric in a sense, right? But still, this is of the order of d square. But in the case of the special case where the features are independent, you just if you have independent features, what happens now? Dependent features, right? You end up with d plus d only, 2d. So in this case, you have the order of d square features. Here you have 2d. So it's a big reduction, right? Big reduction in the number of parameters you need to train for the model. And of course, less the parameters, less the sample needed to train robustly. And it's also computationally quite efficient, right? This is one of the reasons why many a times, even if the features are not independent, people assume the independence of features. People assume that the features are independent. So this is an assumption, right? And this is also brings us the idea of naive Bayes. What's naive Bayes? Naive Bayes is this idea of probabilistic generative modeling, where you assume the features are independent, although it's not independent. Is this idea getting clear? So it makes the life easier in a sense. And also practically in many of the real world problems, if you see, even if the features are dependent and you assume independence, you don't really lose much in quality in terms of accuracy rate or stuff like that. So it is a very good point. Sometimes it's worth considering, right? If you have so many features, sometimes as an engineering solution, people just assume independence. I hope this is clear. Any question on this?
Doctor, I cannot understand the general case, the complexity.
Yeah, what we are speaking about is in general case, what are the parameters we have? We have the prior, which is one value, right? For every class. What we sometimes also donate by pi. Right? And then we have the mean vector mu, which we want the parameters to be trained, right? We need to estimate these parameters. And mu is a vector of d dimension, right? Is this clear? And covariance, which is a square matrix, is of the order of d square features, right? It's a d by d square matrix.
It's right. So
yeah, so what we are saying is the total number of parameters is the order of d square. But in the if we assume independence of feature, the order is d. The number of parameters we need to estimate from the training samples. And also, of course, our computation becomes quite easier, right? So that's what we are saying is many real world problems, people assume independence of feature, although the features in reality might not be independent, but they assume it. And this is the core idea of naive based classifier. It's again a generative classifier, probabilistic one, and you just assume the independence of feature. That's it. Right? So this is something what you get, right? So you might get these contours as ellipsoids, but it's aligned, axis aligned, right? Of course, you might have different spread because the variance is the sigma 1 square and sigma 2 squares are different. So the stretches might be different in different axes, but it's not dependent anymore, right? The features are independent. Is this clear? Shall we go forward or you have any question?
Yes, clear.
Okay, good. Now, what about the probability, the PDF? If you have independence, you're assuming the independence of feature, how does the PDF look like? So PDF would look like this, right? Just let's see this. The PDF of, yeah, what we are saying is P of X given Y is nothing but 1 over 2 pi whole to power d by 2. And what happens to the covariance? The inverse of covariance. So basically, I'm sorry, not the inverse, the determinant, right? So this one just becomes the square root of the thing becomes sigma 1 times sigma 2 all the way to sigma d, right? This is what you get in the base. And now what happens in E is you get E, and what you get here is the summation of, okay, let's say I equals to 1 to D. You have D features, okay, and you have xi minus mu I square over 2, I'm sorry, sigma I square. Is this making sense? So this is what you end up with, right, as a PDF, if you assume the features are independent. Good. Now let's move forward. Another special case is what if your features are independent, and not only that, each feature has same variance. If each feature has same variance, what will happen now to your covariance matrix? You will end up with just sigma square up till d terms, right? Because all the variances are same, and you get these contours as perfect circles, right? Because all the spread in both the axes, in case this is the two-dimensional case, so the spread sigma 1 and this sigma 2 are same, right? Because the variances are same. So you get exactly like this as a contour. And then what happens to your PDF in this case? So what happens is all this sigma, so what you're saying is now P of X given Y is nothing but what? You get 1 over 2 pi again d by 2, and sigma 1 times sigma 2 times sigma d. Now everything is same, so you get sigma to the power of d, right? And here you get basically E of minus xi minus mu square, right? Over what do you get here? So it's basically a L2 norm. So you can just say in a short form is x minus nu. So L2 of that times 2 sigma square, because all the sigmas are same. So this is what you end up with. If you have features which are independent and also having same variance. So this becomes the new simplified form of it, right? Good. So if you have any question, let me know. Otherwise, we move to our next topic in this thing is what type of decision boundaries does this type of classifier has? The decision boundary between two classes. What's the general form of it, right? And if you want to just have a quick intuition into it, just look at the Gaussian PDF thing, right? If you see this, this is something like, if you see all these forms, the general form, right? Even in the multivariate case, it's all same, right? What you get is, if you see this part, it's nothing but x transpose mx. If you have a function x transpose mx and m is a square matrix, what type of what are you speaking about? Any insight into it? What type of function is this? X transpose mx is a quadratic, exactly, right? So what we understand is intuitively, very quickly speaking, that if you have this generative classifier, the way we have right now, the decision boundaries would in general be quadratic. Okay, so to make it clear, right, what are the decision boundaries we have? Let's try to understand this one. And this is also something important, although it might take a little while to go through this, right? So let's try to understand what do we have? We said that the decision, we say how we assign a test sample to a class. We assign a test sample to a class based on the join, right? So we speak about the prior probability of y given a class I, or let's say y equals to 1, the first class, times p of x. What is the likelihood of generating the sample x given the distribution of y equals to 1, the first class distribution, right? This is the general form. And we look at all of them. So we look at p of y equals to 2 times p of x given y equals to 2 and so forth for all the m classes. And the one which gives the highest value, we say this is the class. It belongs to the test sample, right? So what if we look at this in the log domain? Okay. So if we look at the log domain, what happens? In general, what we are saying is this is nothing but, we spoke about this. So this is nothing but, let's denote p of y equals to 1, the prior. Before we used to use pi, but in our equation, we already have the mathematical pi. So just not to confuse with it, I'm just going to say this one. This is prior, p1 times, what is p of x given y equals to 1? It's nothing but 1 over 2 pi d by 2, the determinant, square root of the determinant of the covariance matrix, E of this is what we have, right? So this is the prior, and this is the likelihood of generating x from the class distribution of y. So what if we work in the log domain? What happens now? In the log domain, we can write this as log of, let's assume now we are speaking about class 1, log of p1, right? And what happens to 1 over 2 pi d by 2? Can we write like this? Minus d by 2 log 2 pi. Is this right? And similarly, the square root of the determinant, we can write minus half log of the determinant, right? Now, log of e, so that cancels, and now we are left with minus half, right? And inside we can say is x minus mu transpose sigma inverse x minus mu. Is this making sense? This is what happens if we apply log, right, in the log domain. Any question on this? Okay, now our decision boundary depends on the input, right? So the input in the test sample is what are the variables for the test sample? Who can tell me? In the test sample, what is the thing which is variable and other things are constant? Of course, for the class 1, you have sigma 1, this is mu1 and mu1. Yeah, of course, this is also sigma, the covariance for the first class. So my question is again, in this equation, what is the thing which is variable, which depends on the individual test sample? Any answer?
The X.
The X, right? Those terms which involves X. The other things are in a sense constant, right? Once you have done your training, all those are constant, nothing changes. The only thing which changes is in the test sample, the X changes, right? So what we'll do is just to focus on that, the decision boundary depends on the value of X, right? In that case, that's the only variable here. So let's try to bring that forward. So we are going to say this is nothing but minus half. Okay, we say X transpose sigma 1 inverse X. So we have X transpose. I'm sorry, what happened? Yeah, X transpose. I'm just expanding it. Sigma inverse X. Then what happens? Then we have here minus and mu. So of course, one of the thing we have is mu is there. So we have minus mu transpose sigma inverse mu. So it becomes plus, right? So this one becomes mu1 transpose the sigma inverse mu1. And then we have this internal two terms of mu transpose sigma inverse X, right? So we have two of them. So we have two mu1 transpose sigma inverse sigma 1 inverse X. Is this right? Again, if I make a mistake, please correct me. Okay. So this is what we have. And of course, the other things are there, which is like plus log of the prior P1 minus D by 2 log 2 pi minus half log of the determinant of the covariance matrix, right? Is this okay? Any question on this? Now, let's think about it. We have two classes. Let's limit our discussion right now for only binary classification, right? And that can be easily generalized to multi-class. So we are speaking about either it's a class 1 or class 2. So how we decide which one is there? If let's say it will be class 1 if P of y equals to 1 times P of x given the first distribution is greater than, right? P of y equals to 2 times P of x generated from the distribution of the second class. Is this right? This is how we'll make the decision, right? If this probability is greater than that, then it's class 1, otherwise it's class 2. So what we can do is if you subtract the probabilities from both of them, what do you get? Just see that. So what we'll have is, again, we'll have something similar as a form for the second class, and then we want to just minus each other. So what do we get is minus half. So you have X transpose sigma inverse of X. So you have X transpose sigma 1 inverse X minus X transpose the second class sigma 2 inverse X, right? This is what you're getting from the other one. Similarly, this one this part is a constant, right? Because it does not involve X, so we are not interested in that for the time being. So what we'll have here, we'll focus on this one. So you have minus 2 mu1 transpose sigma 1 inverse X, right? This is minus, so the other one, if you're subtracting, it will become 2 mu2 transpose sigma 2 inverse X. So these are the four terms. The rest, this of course, this minus the mu2 transpose sigma inverse X and these all things, these are all constants, right? It does not depend in the sense it's constant in the sense it does not depend on x. So what we'll say is plus some theta. The only thing which depends on x is this. Is this clear? Good. So if this is the case, let's try to understand this now. So what we can see here, we have x transpose sigma 1 inverse x minus x transpose sigma 2 inverse 1, and this is minus half here. So can we say this one, this part at least? This is the first part, right? Can we say this is nothing but x transpose, okay? You have half, and this is minus, so the sign gets opposite. So you say x transpose half sigma 2 inverse minus half sigma 1 inverse x, right? And what about this one? This one again, the half and 2 cancels, and the signs get reversed because of the negative in the beginning. What do we get here? Now we'll get something like, if you see here, you'll have plus mu1 transpose sigma 1 inverse minus mu2 transpose sigma 1 inverse. This is the another one, and the x is there, times x plus theta. Is this making sense? Anyone has a question, please let me know. So this one,
I think the first x is x transpose, not x, right? The first x in
which
the
one?
equation.
Yeah, I'm sorry.
The first
this is
x,
transpose.
yeah.
Yeah, this is x transpose. Yeah, thank you. Yeah, and any other question?
Doctor, I think you missed the sigma here. Must be 2 instead of 1. The last sigma.
Which one?
Which one?
This one?
This one?
Yeah, it must be 2, I think.
Yeah, you have 2, but the 2 cancels with the half, right? Once you open the brackets.
Okay, I get you, Doctor.
Yeah. So what happened? I'm sorry. What did I do? Yeah. So what happened here? Let me see. Yeah. So this is what we have, right? Again, please go through it and let me know if anything is not clear. Let me know. Okay. So this, in the general form, we can say.
No, Doctor, I think the last sigma, the subscript, must be 2.
Yeah. Yeah, I'm sorry. You're right. This is 2. Yeah. That's true. Yeah, you're right. Any other observation or any other point here? Is it clear, all of you? Okay. Now this one, what we can write in general form is x transpose mx plus w transpose x, right? Plus theta. Now what we look at it, because m is a d by d, right? So it's a d by d square matrix, and this is mu1 times sigma 1 inverse. What do you get actually? You get here, you get 1 into d, and this is d times d, right? So basically you end up with 1 into d. So it's a vector, right? It's a vector. So you get this w is a vector and x is of course the feature. So basically this is, so what we are saying is m, in this case what we are saying m is nothing but half sigma 2 inverse minus half sigma 1 inverse, and w, sorry. And what is w here? W is nothing but mu1 transpose sigma 1 inverse minus mu2 transpose sigma 2 inverse, right? So in this case, actually what happens? This becomes, if you see this, okay, this becomes the quadratic term and this is the linear term, right? This is how our equation, and these are some fixed values, right? This theta depends on other parameters you have estimated. So this is what you end up with. So it's, and again, of course, linear is a special case of a degenerative case of the quadratic. So now what do we understand from this discussion? We understand that generally speaking, what happens? The boundary of Gaussian classification, what we do, the normal generative modeling is going to be a curve. It's a quadratic boundary. Is this clear? So this is going to be the thing. So what you want to do is basically, if in a sense, what we can say here, okay, I'm sorry, I was writing X transpose MX plus W transpose X. If it is greater than some constant, it's one class. It's one of the other class, right? So this is basically how you deal with it. So it's a quadratic decision boundary. So generally speaking, you have a quadratic decision boundary. Now let's take some special examples. Okay, let's take this example here, which is, and again, this is very important to keep in mind. This is very important to understand why we are saying, generally speaking, the decision boundary would be a quadratic. Okay, and what do we mean by this, M and W? Now, if you go here, okay, now we are going to speak about same covariance. So assuming that you're doing classification between binary classification, assume, and then you have same covariances. So the covariance matrix of both the classes, the sigma 1 and sigma 2 are same. What happens now? What will happen? Think about it. And assuming the priors are same. So in a sense, what we say is P1, the prior, or what we say pi1 equals to P2. The prior is same, and you have same covariance matrix. What type of decision boundary do you get? What do you think? Look at this. So we said, again, I'm writing it here maybe. So we say the general form of the decision boundary is X transpose MX plus W transpose X. This is the general thing, where M is nothing but, what do we have M? M is nothing but half sigma 2 inverse, okay, minus half sigma 1 inverse, and W is nothing but mu 1 sigma 1. So you have mu 1 transpose sigma 1 inverse minus mu 2 transpose sigma 2 inverse. So what we are saying is, what if both the covariance matrix are same? What type of decision boundary do you think you'll get? Any answer?
It should be aligned now.
Yeah, why? Because M becomes what? M becomes 0 now. Sigma 1 is
Yes.
sigma 2. So half sigma inverse minus half sigma inverse, that cancels out. So this quadratic form, this becomes 0. So the whole decision boundary is just dependent on W transpose X greater than some theta. And if assuming that the features were independent on all the variances were same, just assume like this. So in this case, you'll have the PD of two classes with same covariance. We already spoke about this. Again, my drawing just assume that is the same scale, right? So what happens now? And again, both the priors are same. So the decision boundary will be exactly in the center, right? This will be your decision boundary. And assuming this is exactly the center of two means, right? So this is your decision boundary. Okay. Similarly, assuming that again you have independent features, same covariance and everything. Okay. So two classes have same covariance, features are independent and same spread. Now, what happens if, let's say, P1, the prior of P1 is greater than P2? What will happen? What will happen to the decision boundary? Will it still be linear or no? If P1 is greater than P2? What do you think? Any answer? So again, I'm repeating, we have same covariance, but the prior of one of them, one class is higher than the prior of two. So the first question is, are we going to get a linear boundary or no?
Yes.
What do you think? Yes, right? Because still the covariance is same. So X transpose MX, that is still 0. So your decision boundary is still dependent on W transpose X. But because prior of 1 is higher than that, the decision boundary will not be exactly on the center. So assuming this is the class 1 and this is class 2. So your decision boundary will be shifted towards this one, right? So it will have more area for class 1, the wider area, because P1 is greater than P2. And what happens in this case? Think about it. Now, again, your covariances are same, but the features are not independent. So assuming you have some tilt. And both of covariance are still same, but the features are not independent. I'm sorry, they're dependent. Now, first question, are we going to still get a linear decision boundary? And the answer will be yes, right? As long as same covariance, the decision boundary is linear, but because there is a tilt, the boundary will also be tilted. Same thing. And still you have the same rule, W transpose X greater than or equal to some theta to make your classification decision. Okay, if you have any question, let me know. Now, what about if the covariances are different? What happens if you have different covariances? What will happen now? So assuming now, okay, that you have two distributions, again, binary classification. I'm sorry. So I'll use the green. So assuming you have, right, these two features, good. And this is the another one. Okay, so you have different covariances, and assuming the covariance of class 1 is more spread than the covariance of 2. So the covariance of 1 is larger than covariance of 2. Okay, so what sort of decision boundary we are going to get? First of all, are we going to get a linear boundary? Yes or no?
No.
No, right? Because now the covariances are different. So you're not going to get one as the linear boundary. You're going to get some sort of quadratic boundary, but because covariance of 1 is larger than covariance of 2, you'll get a boundary something like this, which says everything inside this is class 2, and this is class 1, and even this is class 1. So if a sample is here, is class 1. Does it make sense? So all this is class 1, including this side, the opposite side. And this is inside is the class 2. This is class 2. Now, to just make sure that this makes sense, let's look at the 1D case, right? Assuming these are the 1D Gaussian, what we are saying is you have one which has a higher spread. I'm sorry, this was too high for the screen. Something like this. And one is a narrower one. What happens here after this area? So you have all of this is one class. Let's say this is C1 and this one was C2. So all this is C1. But again, here also you get this region is again C1, right? This all is C1, even the other side. And this is the only part which is C2. So this is what happens. You get this type of boundary and the opposite side is also C1. But in general speaking, the boundary would be some quadratic.
Doctor, what is the condition here in this?
The condition is, of course, both the covariances are not same, and one is more spread. One is higher variance, the covariance than the other one. So C2 has is a narrow one. The C2 is the narrow one. So it has its decision boundary a quadratic, and because this one is more spread, even the opposite side is it is the same class. So this is C1, this is C2 class, and all the other thing is C1.
So is C1 has more probability, or
what is the thing is it's more spread, right? So again, let me draw it again. I'm not sure if it's clear or no. So we have this as C1, more spread, and C2, let's assume, is more narrower. So this is one dimension. So what happens if the X of the test sample is here? Which class will you assign? Let's say this is C1 and this is C2. What happens if your X is here? Assuming the prior can be taking a little bit of influence. Assuming for the prior right now is same. Assuming P1 is the prior of 1 is same as prior 2. So depending on that now, if X is here in the test sample, which class you are going to assign?
C1 definitely.
C1. Similarly, X is here, you will assign C1, right? Until approximately here. All of this is C1. But then from here to here, what's going to happen? You're going to assign C2. But what happens if the X is here? If the X is here, this is again
C1.
C1, exactly. That's the whole point. That's the whole point, okay? So this is what I'm saying. So in the two-dimensional case, you'll get something like this. And the other thing, the overall, because C1 is more spread, so even in the opposite direction of C2, you get the C1 class. Okay, any other question before we move forward?
So in this case,
Okay.
we'll get a quadratic decision boundary.
Yeah, it's a quadratic, right? You can see it's already an ellipse, so it's a quadratic decision boundary. And in general speaking, it's a quadratic boundary. In general speaking, it's a quadratic boundary, as long as you have variances of the classes are not same. So now we go to another topic, if there's no more questions, is the idea of this smoothing. What we say as somebody else, yeah.
Sorry for interruption. The last scenario, Doctor, what is the condition exactly?
Is anything. The only condition is the covariance of a class is not same as the covariance of another class. So it's some sort of quadratic boundary, depending anything, any situation, how it is.
The probability is same, or?
No, we are saying the covariance of one is different than the covariance of two, in general speaking. So you'll get a quadratic boundary, which is this one. The form is this one, right? The form is going to be this form, right? X transpose MX plus W transpose X. So it's some quadratic boundary. I'm just giving this as an example. So generally speaking, in generative idea, if the covariances are not same, you're going to get a quadratic boundary.
And C1 is wider, yeah?
And
C1 is wider, sigma.
yeah, in this case, C1 is wider. If the C1 is narrower, you get something like this and so forth. So that will change, but the form would be some sort of quadratic boundary. Okay. Now we come to another important topic, as somebody already pointed out to us before. What happens, because we are going to take the inverse of the covariance, right? What if it's singular, right? So you cannot take inverse of that. In a sense, let's try to motivate what is going to happen. Think about this. You're doing digit recognition. And let's say you are training your class 1. So this is your class 1. Another sample in training. This is class 1. Another sample of training. This is class 1 and so forth. You have a number of samples of class 1. And based on that, you train your classifier, right? So you train the mean and all the covariance, everything you're training it. Now, assuming if it was the same thing as the MNIST, you have 28 by 28, your mean vector X is going to be 28 times 28, where each point is a feature. Now think about this. These are the samples, okay? Now, you get a sample in the test. This is test now. You get a test sample. Okay, okay, no reason to make it bigger. You have a 1, okay? And of course, you have already training other classes as well. So you have samples for class 2. Okay, maybe a sample for class 3 like this. And so forth. You have different sample. And now in the test case, assuming there was a pixel here in the corner, the first pixel, the first X1 is a black pixel. For some reason, it's a noise or some scanning problem, something. But in training samples, you never had this pixel on the corner, never had this ink pixel on the corner. It's always empty. In a sense, it's always white. So the feature X1, right? What is the mean going to be in that case? Let's assume it's a grayscale image. What is the mean of X1 for the class 1? Any answer? It's always perfectly white. So you have the mean vector is X 786 or something, right? I don't remember, 28 cross 28. You have this vector for the mean. Now, what is going to be the mean? Because it's always in all your training samples, it's always perfectly white. Your mean is going to be 255. Is this clear or no? Now coming to the covariance matrix for class 1. Again, it's a very big matrix, 786 by 786. But what is interesting for us is the variance here. Now this variance, what is the variance of the first feature? What do you think? What will be the variance here? Any answer? All your samples, you have the first x1 is 255, always. It's always a clean image. There's nothing noise in the corner. So the variance or the standard deviation would be what for x1? Any answer? Is it going to be 0? Yes or no?
Yes, because it will always be.
Because it's always 255,
right,
so there is no standard deviation, no variance, right? Everything is 0. Now what happens is if you have a test sample with this spot here, although it looks like 1, very clear, it's a very nice example, so it matches with 1, but it will try to predict the class being, for example, 3. Why? Because the moment you multiply this probability, this is 0, everything becomes 0, no chance. You don't want that to happen, right? And another way to look at this is this one is going to be a singular matrix, right? This D by D matrix is going to be, you cannot find the inverse of it. So what will happen is you want to do is the smoothing, the idea of regularization. We are saying it's overfitting. There is no sample which has a noise here, so it's overfitting this idea. So what do you do as a solution here? You say after you have learned the covariance matrix of every class, you say a covariance matrix of any class equals to what? The covariance of matrix of any class, the same class, plus C times an identity matrix, which is again the dimension of D cross D. And what is C? C is a very small scalar value. A small scalar value, right? 0.1, 2, 0.5, it again is a hyperparameter. So what happens because of this? Anything which is very small or 0, what will happen to that?
The inverse will be very hard.
This is the identity matrix, not the inverse, right? So you are going to have C. So at least what you're saying is the variances is at least C. C times the sigma, whatever, sigma I square, sigma 1 square, C times, right? Is this, I'm sorry, not times, C plus, right? Because you are adding an identity matrix, right? The identity matrix is this one. You have all the ones in the diagonal and the others are 0. So your original covariance matrix, you add C times the identity. So you get everything at least C on the diagonal. So now you save the problem of singular, so you can find the inverse of it. And also at the same time, what you're doing is you're smoothing it, a form of regularization, so that if you have this type of scenario, it does not just rule it out just because you never saw that before. It's not ruling it out. So you have at least what I'm saying is C at the diagonal, at least a C. So this is the idea of regularization in this case, right? The idea of smoothing where you add the small value C and add the diagonal elements of the covariance matrix. Any question on this?
Yeah, Doctor, I think there is a typo here. It should be 786 instead. Must be 784, I think.
Okay, yeah, I said I didn't do the calculation, so maybe 704. Thank you for reminding me. This is 784, right? You're right. So it could be. I did do the multiplication. So yeah, 28 times 28. Yeah, 8 8 are 64. So you're right. 784 makes more sense. So 784 by 784. Good. So is this idea getting clear of smoothing? So smoothing is basically a regularization technique. It avoids two things for you. Actually, it's related, but conceptually, it's all related. But two things what we are saying is it allows you to have the inverse of the covariance matrix, because now the covariance matrix is no longer singular, right? And it's basically a regularization technique. So you make the covariance matrix more regular, right? And it tries to avoid this type of overfitting. So if you didn't find a specific example, you just don't rule it out because you have never seen exactly something like that. Okay. So if you have no question, I'm going to move forward. And if you have a question, let me know now. Okay, so what about in the case of multi-class? Again, multi-class class is a very natural extension in this generative modeling, right? So basically what you're doing is you're just training the priors and you're trying to train the posteriors, right? I'm sorry, the likelihood. So for every class, you're going to say, So you're going to train the parameters for them. So you have. So I'm assuming you have M classes, right? Or let's say K. Normally we use the word K here. So if you have K classes, you just have K priors and K different probability distributions for each class, right? Y equals to K. And again, you find the likelihood of a test sample being generated from one of them, and the one which has the highest probability, the prior times the likelihood, you just say that's the same class. So in a multi-class, it's a very natural extension in here in this case. So you don't have to do something like 1 versus all or 1 versus 1. It's just basically probability and find which one is most, the higher, the probability is higher, the joint distribution is the highest value. That's it. Is this clear? And of course, if assuming a special case here, what happens if you have 3 classes or 4 classes, anyone, and all of them have same covariances? What happens if all of them have same covariances? So you get some sort of, I don't know how to draw it, some sort of linear boundaries, right? So this is the resultant boundary you get, something like this. Okay, good. So what else? Yeah, there's one last topic for the generative idea. Is there some other extensions to the idea here? One of the extension we already spoke about is in the which distribution to fit. For my training sample, we said if there's no another reason, we might take the Gaussian as the normal distribution, right? The normal distribution. But what if there are some strong reasons not to take it? So we took the example, what if the X features are all positive values? So we might take gamma distribution. Or what if my X's are in some certain interval? We might take a beta distribution or other distribution, right? What if the X's are only binary values, either +1 or -1 or 0 or 1? We might take Bernoulli distribution. So distribution, the choice of distribution is one important thing we can also think about, right? So sometimes it's good to not use Gaussian, use something else, which might be more accurate representation of the real problem. Okay. There's another thing is also we spoke about the idea of using assuming the features are independent, and that's also a general idea of the graphical models, probabilistic graphical models, right? The classification. So what happens here is this. In the graphical models, let's say this is the class, right? So we put these features, right? X1. So these are components of the feature: X1, X2, X3. Let's say XD. In the one we saw where we are not assuming any independence between the feature, what we say is that these features contribute to the class because it's related to the class. These are meaningful features in a sense. Okay, and all these features are related also. There's dependence, right? So we're not assuming independence generally speaking. So features are generally dependent. So there is in the graphical model, the probabilistic graphical model, we have this line between the nodes. In case of naive Bayes, what we say? We are assuming independence. So what will happen in the naive Bayes is we have X1, X2, I'm sorry. Similarly, we have XD features. And these features are meaningful in a sense that they contribute to the classification, but there is no link between them. So in a sense, the features are completely independent. But then using these two ideas, we can have a general probabilistic graphical model where we have a C and we have these features X1, X2, similarly XD. And what can happen is, let's assume there's X3. Of course, these are all meaningful in a sense, they are contributing to the class, but for example, X1 and X2 is related, but X2 and X3 is not, and there is another X4 which is also linked to the C, and X3 and X4 is related somehow, and X4 is related to X3. So you have some features which are dependent, some features which are independent, right? So you can have this type of general structure which comes under the graphical model, right? And how you build this is another thing. You can use domain knowledge, you can use the training samples to decide that these features are independent or no, and then you can do classification using this idea. So